something, you expect it to come with a data sheet. And guess what? Guess what? It didn't. So what I was going by, we order it from a company called Jamico. We do a lot of business with Jamico Electronics, guys. It's, and Jamico's really good about providing data sheets too.
Oh. You've got a connector like this.
Yeah, but you can take it off. It's not. So this is when I went and ordered it. And down here it says what? I'm sorry.
This is 64.
Yeah, but that's what got us wrong. That's what got us. So I think I came up with 60 just by counting and put my phone on 10 seconds, and I started counting. I might not have started counting right on time, and then I might not have ended. But I counted for 10 seconds and came up with 11 revolutions, and that came up and gave us 66. But when we did the math, we came up and got 27, which is a really, really big error. Is it coming? Oh, I got it connected. It's nothing but the mechanical drawing or the drawing that a draftsman would look. There's nothing there. So I took for granted that it was 64, and then we realized that was wrong, and then I thought they were counting the positive and negative edges, and that's why we halved it to what? 32. So what I did when I got home, I did a little research on it, and I did find sort of a data sheet, but it's good enough for us to. It's a lot better than what we got, and it's posted. It's up on Blackboard, by the way. And so gear motor 131. It's not actually 131. So this is what I found about this. So it's called a motor gear with 64 counts per revolution. But that's not exactly true. It says the gear motor is a powerful 12-volt brush DC motor with a 131.25 to 1. So we were using 131. We used 131, but it's actually 131.125. And then it comes up here, and it did give us the all the gear ratios and the torques and everything. Then it gave us the color code, which is really, really good. Of course, I already had that. And then we come down to this last paragraph right here, which is what is the Hall effect sensors, an input voltage of VCC, which is what we call the power supply in digital. It's kind of misleading here too, because in digital, if we use the term VCC, it is plus 5 volts. So in digital, we have different in transistors. VCC is just a power supply that connects to the collector. And digital VCC is what is plus 5 volts. But anyway, between 3.5 and 20 volts, and draws a maximum of 10 milliamps. The AB output for square wave from 0 to VCC. So whatever you will put on VCC, then that's what you should get amplitude of pulse. Makes sense? So the frequency of the transition tells you the speed of the motor, and the order of the transition just tell you the direction. By counting both the rising and the falling edges of both A and B, it's possible to get what? 64 counts per revolution. Of the motor shaft, using just single edge or one channel, which is what we were doing, is what? 16 counts per revolution of the motor shaft. So the frequency of A is above oscilloscope captured at 16 times the motor rotation frequency, which would be gear ratio. Are we okay? That makes sense. So instead of using 32, we should have used what? 16 times 131.25 instead of 131.1, right? Y'all understand? Yeah. Yes or no? So I've added this to the PowerPoint and I've uploaded it. So this is what we have. Our gear motor with a quadrature encoder. So we have a gear train, or something they call it the gearbox. Then we have a DC motor, and back there on the back we have the encoder. The wiring for the whole thing comes out of the back of the encoder. And the Haltech encoder is a 1.31, 0.25 to 1 gear motor. Output shaft pulses per revolution would be 16 times 131.25, which would give us 2,100. Everybody okay there? Everybody makes sense? Everybody okay? Motor's DC, it says you can run it above or below. They recommend that you don't run it below it, which is all true because the motor starts pulling more current. And if you pull more current, then the motor would run faster. But what you want to do on a DC motor is you don't want to run it higher than its rated voltage, because what you do is you reduce the mean time between failures for the motor. So the motor wouldn't last as long. And so these are our formulas. So instead of using 16, instead of using, I think we came up with, what was ours? Yeah, but that was totally wrong, because we were using 32. Right, you understand? Because I thought they were counting both of them, but actually they're counting all the edges. Okay. On 2100, 4200 output shaft pulses per minute can be obtained by counting the rising and falling edges of one channel. 8400 output, so we were using 4200. 8400 output shaft pulses per revolution can be obtained counting the rising and falling edges of both channels. I was trying to figure out the circuit. I can figure out a circuit that do that. Like that. So, formulas for RPM would be frequency over 2100 times 60. Now, what we did, if we're going to use this same thing all the time, it just wouldn't make sense to use these two numbers all the time, right? You understand? So what I've done is I went ahead and solved for what 60 over 2100 would be. It's going to be able to 0.0286. So anytime I get 60 over 2100, which all these would be, I'm going to substitute that for what? 0.286. And that's what we would do in a PLC. We wouldn't go through a division program and a multiplication program when I can do it all with what? Either a division program or multiplication. Does that make sense? So I can take the frequency and multiply it by 0.26. And where did I come up with 0.286? Yeah, I just moved this over here, put it in 60 divided by that, right? 60 divided by that. And actually it's a long number, but we got to give up. The error's not going to be that big. But in the PLC, guys, we can carry it out a long way. An integer, a real number, which in Allen Bradley, they call real numbers, they call them floating point numbers. Floating point numbers. Siemens calls their floating point numbers, they call them real numbers. So we have integers, and then we have real numbers. Now, what's an integer? It doesn't have a fractional component, right? I understand that. And then real numbers are numbers that can have a fractional component. Y'all understand that? They don't have to have, but they can. Real numbers also means when you exceed the range of the numbers, then it'll shift into engineering notation, just like your calculator. So when you exceed that range, it automatically shifts into engineering notation. Now, engineering notation is great, but what's the problem with engineering notation? It's what? No, what? Scientific notation. What's the problem with scientific notation? Yeah, but we're still going to have a certain, we will never go out to an infinite number of digits. Never. Right? You understand? So as long as I'm using integers, then I've got a perfect number. Right? You understand? Until I exceed the range. They're going to have to give up somewhere where they're going to say, okay, this is the amount of resolution we have. It's just like engineer notation. We want you to round to 2 decimal points. As soon as I say round, what does that mean? Huh? It's not an accurate representation of the number. Most of the time it's close enough, but it's no longer an accurate representation of the number because you just what? You round it. So the problem with scientific notation, of course, is that the number is not, the bigger the numbers, the less accurate they're going to be, because the more digits you're going to have to drop, right? You understand that? Yes or no? It's just like engineer notation. If we come up and say, okay, what's the square root of 2? Well, what's the square root of 2, guys? Anybody know what the square root of 2 is? How far does it go? We don't know. It's a real number. I mean, we can represent I'm sorry, this is what we call an irrational number, which means a real rational number is a number that we can't represent with a fraction, an integer fraction. Like pi. Pi cannot be represented with something over something, right? You understand that? To come up with pi, because pi is an infinite number. So what we'd have to do is, as soon as I shift this into engineer notation, let's see, does this guy do engineer notation? Probably not. But your calculator, as soon as you shift it to engineer notation, then it's going to start doing what? Rounded. Okay, you understand that? So real numbers are okay. I think Alan Bradley uses a 32-bit number, but 24 bits are used for the weight of the number. And then the other bits are used for the exponent if you need it, right? You understand that? Something raised to some power. Are you okay? Does that make sense? So if we could represent up to 2 to the 24th using real numbers, and it would still be what? Accurate. But as soon as we go above 24 bits, not bits in a number, then all of a sudden we lose our accuracy. Everybody okay? Does that make sense? So Siemens, I'd have to know. I got the ranges somewhere. I put those up there, guys. Some of them I don't quite understand. But Siemens, so Alan Bradley, I don't know about the 5000 software. That's something I need to start researching. But I know the 500 software, floating point numbers are 32-bit numbers. It lets you go up to 2 to the 24th before you switch into engineering notation. That makes sense? And then after that, it comes up and then it wouldn't be accurate, right? That makes sense? Siemens has a long real number, which is 64 bits, so that's going to be a number that you don't worry about. So when we did our motor, we spun our motor, we looked at our time on our oscilloscope. Let me see if I've got this wired up. I don't quite have it wired up yet. So ground for the encoder is black. Oh, I'm sorry. Brown for the encoder is, you can't see the color. I know it's not black because that's the motor. Okay, here we go. I just didn't go. So ground for the encoder is green. And we're going to hook this up to a PLC. I'll show y'all the, and then my encoder output. So what I have over here is I have 3 powers. Why did I have to use 3 different power supplies? Yeah, so the PLC runs off of 24 volts. I needed one to run the motor so I could adjust the speed. And then I needed another one to run the, I have a 5-volt output, but according to my, I don't know exactly where my PLC recognizes a 1 or a 0. I tried to look at that. The inputs on my PLC are digital inputs is the way we have them set up, and they're 24 volt inputs. I'm sure it'll recognize 20 volts, but I don't know if it would recognize 5. I couldn't find that information on where the threshold is on the inputs to determine where the switch occurs. So the ground for my encoder, or the common for my encoder, is green, right? So y'all remember the time we had, the time we were using, and all we're going to do is look at one. We don't need to look at both of them. Oh crap. That's not good. I hope I didn't just burn up my encoder. I have it set blue, right? If I ran this thing at 12 volts, the output shelf is supposed to run at 80 RPMs. How fast would the motor be running if the output shelf is running at 80 RPMs? Well, I would take the 80 and I'd multiply it by 131.25, and that would give me the speed of the motor. I'm sorry, that would give me the speed of the pulses. How fast would that be? Okay, so that motor's out there running at 10,000. It's got a frequency of 10,000 hertz. There's no way in the world a software counter would keep up with that. And they realized that in PLC. So every PLC that's recently came out, and I don't think the 504, SLC 5, the SLC 504s have a high-speed counter inside it, but we could get a high-speed counting module. You understand that? PLCs for the last, so the 1100s have a high-speed counter, and the 1200s, which is what we're playing around with, has a high-speed counter. A high-speed counter, guys, is a hardware counter. So one advantage that hardware has over software is it's always faster. Always faster. But the problem with hardware is you really can't change it, right? You understand? With software, I can make my computer run this program. I can make it run Word. I can make it run this. I can make it run that. If it was built into the firmware or the hardware of the machine, then I couldn't run anything, right? You understand that? Does that make sense? So what we do is, this is the name of the program here. We're going to go ahead and open this program. y'all that hadn't had PLCs, it's basically you've had motor controls. And what's nice about PLCs is we program all those things into it, except for inputs and outputs. So hopefully, and I know this works because I use a function generator at the house to simulate. I didn't have 3 power supplies at my house. So I used a function generator to simulate the encoder, and it worked great. So Siemens calls their main program OB1. This should be like ladder 2 for the RS logic. You had PLCs. And so guys, this is a program. So we don't have a high-speed counter instruction, but we have a CTRL, which is the control of the high-speed counter. Does that mean this is the way we configure the counter? And so this is what it's counting, this enable. CV is every time we reset it. And then the NCV, this would be the new value. So what I do is I reset the counter. So I've got this thing running on a 2 hertz clock. Why 2 hertz? So we're going to let it count for 1 second. So when it's true, it's counting. When it's not true, it's not counting. Does that make sense? And then what I do is I clear it on the logo when it's low. I'll let it count for 1 second, then I clear it for 1 second. I'll let it count for 1 second, I clear it for 1 second. That makes sense?
Where's the signal at?
Okay. For one thing, as soon as I use the control high-speed counter, the counter is understood. So this is not the input to the counter. The input to the counter is hardware. So it's seeing the output of the encoder and it's counting the encoder. What the enable does, it enables when it counts. So if this goes high, the counter's enabled and it starts counting my encoder. When it goes low, so I let it count for 1 second. Right, you understand? And then I don't let it count for 1 second. That makes sense. Then what I do is, once I count it, then I tell it to load whatever value I put right here. Okay, so see what I'm saying? So you're not seeing the count. This is not the count.
I was asking, what is 2 hertz?
1 second on and 1 second off. That's what 2 hertz is. So 2 hertz is it's a digital square wave. What that means is it's got what we call a 50% duty cycle. So if I use 2 hertz, then it would be high for 1 second, and it would be what? Low for 1 second. And then when we clear it, we're also moving it. So this is my encoder out. And then this is my multiply. I'm using real numbers, which means these are numbers that can have fractions, right? These are the 2 numbers. So my first number is coming from this guy, right? That end rotation. And then this is my second number. I'm using a constant, and that's my transfer ratio right there, right? Okay. So this guy right here is going to show me the what? The actual RPM. Now, whether this works with 5 volts, I don't know. We'll find that out. But what I'm going to do is I'm going to take the output of my encoder, which I have my scope hooked up to. Then I'm going to hook it up to my PLC. And then I'm going to take my common, my encoder common, which is green. Yeah, don't get messed up. And it's not working. So what I got to do is get another power supply because my PLC does not represent 5 volts. It don't say 5 volts because it's a 24 volt input. Wait a minute, one of my leads came on. So white is my A output, right? Y'all didn't write that down. I know y'all didn't. Yeah, A. So white, I'm using the white, so I'm using the B output. But you got to understand A and B are moving at the same frequency, right? They're just 90 degrees off phase. I can move it over. And then my encoder common is green. And my PLC don't like it. Make sure I'm not doing something. It's still there. I can get my scope to latch on to. And latch on to. So when we take a break, I'll go down there and get another power supply. There's nothing I wanted to show y'all before y'all go to lab. And since there's a lot of people not here, I guess they decided to take the whole week off. And one whole group, I don't know what I'm talking about, didn't show up last lab. So guys, I don't know what y'all are going to do on your labs. Of course, that's not my problem. And we went over a lot of stuff that's going to be on the test today. So, let me pause this for a minute.
Yeah, this right here is on mine.
Yes, it is. And that's why I told y'all could go and look at that. You know. I didn't use all three. Sorry, I can't count. One day I'll learn how to count. So this is a supplement. It basically tells you basically different types of terms, right? Motion, corrosiveness, which I need to go through and make sure I add all these. Density, physical state, movement, conductivity, abrasive, sensing distance. And I don't think any of those terms was in your review. They do need to be in the glossary for this. So I've uploaded a new glossary, and like I think I told y'all, the glossary is a document that's constantly in flux. I do know there is something on the test about charging, discharging, and then level control. So what would you think a charging system would be? So we can maintain it between a height. We can maintain it at a height, maximum height, or we can maintain it at a low height, right? So what would you think of charging? Yeah, but just what do you think? Would it be maximum? Would it be minimum, or would it be both? When I charge something, so when I charge a battery, so think about charging and discharging the battery. Is charging a battery and discharging a battery the same? Same. Huh? Yeah, so charging would be when we try to maintain a level at a maximum value. So what would happen is we'd charge it up until it gets to a maximum value and then we'd cut it and then we'd stop. Right, you understand? And then we might use a timer or something and then we'd wait for a while and then we would do what? We would charge it back up. Right? Everybody understand that? Or does it make sense? The level switches detect the response to the level of a material in a tank. Normally the response to a charge or discharge to the tank. Charging the tank is also known as pump control. In a charging application, the level in a tank is maintained. The liquid is removed from the tank. The level switch signals the circuit and adds liquid, right? You understand that? Until it gets up to a what? Maximum, right? Liquid may be added by opening a valve or starting a pump motor. The liquid is added until the level switch detects the correct height. Flow is stopped when the level switch is detected to the correct light. Liquid is added when the level switch is no longer in contact with the liquid. So what they're saying is we bring it up, and as soon as it drops down, then it's going to constantly do what? Up, down, up, down, up, down. I've seen this used before. Sometimes they'll use a timer so they don't trip it as soon as it drops below. They give it a certain amount of time and then they'll bring it back up. But what we're talking about is we only have one level switch. And it would be where? It would be up toward the top of the tank. And what's it also called? Pump control. So that's what we're doing. We're now actually controlling the pump or whatever it is that's adding material to our level.
All right. This long code.
Well, what would happen, normally open used in the charging circuit. Well, yeah, that would be normally closed. And that's the symbol, by the way, for a float switch. And this is what we're going to have to learn. I need to put a bunch of symbols on the next test, which is I've been lax on that. I need to make sure y'all do that. So we've had a limit switch. Everybody understand? We looked at the symbols for a limit switch. And then what was the other one we talked about? The proximity switches. Those are pretty standard until we get to these guys, which is the float. This is the symbol for a float, right? Okay. And we want it to be normally open when it gets up to a certain level. I don't think that's wrong. Okay, so what do we want to do with this? We need to go back and double check. But what do we want to do with it? Right now, the liquid is below the point. What do we want to do? That's right, but that would be on the. I don't think it's an error up here. Oh, okay, but it's a pump control. It's a pump control, so that would be. So this is a normally closed switch. So this is right. This right here is wrong. I understand. So it needs to be, and the symbol's right, because what we want to do is when it drops below the level, we want it to do what? Charge up until it hits our sensor, and when it hits our sensor, it goes opens up and cuts off the pump. Now trying to maintain it at a level would create oscillation, right? Why would that be? Yeah, if we're constantly feeding out, then we're going to be constantly turning our motor on. And if we're right at the level, then it's going to be off on, off on, off on. If we drop it down real fast and then turn it on, then we have no problem. But trying to maintain a certain level would cause oscillation. Huh? We can put a timer on there and let it discharge for a certain amount of time, especially if we know the rate. If we use variable rates, the timer would not be good. So the timer is going to depend on its open loop. So if I run it out real fast, then my timer might do what? Might not time out before I'm done. So what we'd have to do is we'd have to set our timer for the fastest rate that we discharge. And then we might have a problem with it oscillating, right? But this is called a charging system, also called a pump control, because that's what we do, is turning on the pump. Then we have a discharge system. What would you think a discharge system would be? Yeah, so a discharge system is going to look at so this is a discharging system. Discharging tank is also known as a sump control. Discharging application. When liquid in the tank is removed, once it reaches a predetermined level down at the bottom, so this guy's going to be at the bottom, right? So it's going to be a normally open, right? And then when it drops below the level, it's going to turn on your pump or whatever speed it is and fill it back up, right? Makes sense? I'm glad you noticed that. This is, you might have noticed it before, because like I said, I can't find my book that's got the corrections in it. So, but that's one correction I need to make sure I've made. So here we use a normally open. The other one we use a normally closed. That is on the test. So here our level switch would be down at the bottom of the tank. And when it drops below that, what we do is we turn the pump off. And then we let it do what? Fill back up, and then we turn the pump back on. Okay, understand that? Or whatever speed, that is right, that is not.
Normally open.
No, this is right. It was wrong. It was right. It was right. It was wrong on the pump control. It's right on the sump control. And the symbol they used was right. It's just that when they gave the nomenclature or gave what it was, they used the wrong thing here. Looks like they did a copy and a paste with this right here because it's even the same font. But that little bubble down there indicates this is the NC. It's right in the diagram that you're going to wire up. So here's the diagram you're going to wire up. Okay, y'all see that? And it's right. This is the right symbol. If we look at the other one on the diagram you're going to write up, dang, I closed it out. See, so this symbol, the symbol's right, but the nomenclature's wrong. But down here in the actual one you're going to wire up, it's got what? Yeah, it's got the system uses the normal code level switch. So pump control uses what? Normally closed. Sump control uses normally open. And then we have the next one. What do you think we're going to do with the next one? Yeah, we're going to use both of them to set a span, right? But you run into both of them. The more stuff, the more sensors you add to an application, the more expensive the system becomes. Does that make sense? Huh? Yeah, but if I can get by without using the sensor, by George, I'm gonna get by without using the sensor, because not only does it add a sensor, it adds the wiring for the sensor, and it makes the control more complex, right? Does that make sense? So the more complex the control is, the more it's going to cost them. So people wonder why we still use open loop. If a company can get by with open loop, by George, they're going to get by with what? Open loop. And you'll see that on a couple of our manufacturing lines over there. There's certain things that are open loop. I wish they wasn't, but they are, right? So what I would have to do is I would have to have another input available on my PLC. I would have to put the sensor out there, and then I would have to wire it, and then I would have to rewrite the program to monitor the sensor. And I'm not going to do that. And hopefully I can understand why. So 3 is going to be what? Yeah. It's going to be a 2-level control system, right? So what we'll do is we'll have a normally open at the bottom, we'll have a normally closed at the top. So now we're gonna maintain it between a range. And this is the most efficient if you can't get by the other way, right? You understand that? Two-level control, the distance between a high and a level must be considered. The distance set may be small or great in applications using one level switch. The distance is small, the application using two level switches, the distance can be any length. So here what we're going to do is we're going to put a normally open at the bottom, normally closed at the top. And now we're going to have to monitor both of those. And so we've added a memory circuit. Why do we have to add a memory circuit? So this guy at the bottom closes. When it gets up above that bottom sensor, it's going to do what I'm inserting. This guy here closes, so this guy's on the bottom, this guy's on the top. Let's see if this is right. So the normally closed should be the sump. The normally open should be normally closed. Yes. So yeah, this is another error. So normally closed high level, right? Yeah. It's normally open should be what? Now, this is not the symbol for normally closed. You see what the guy did? So what's the symbol? Let me bring up PowerPoint. So I know, I wish I could have found that because we're going to have to go through this again. Because I think this is backwards too. So this is a symbol for normally open, right? You understand? And this is the symbol for normally closed. Now what they've done is they've come over there and drawn it like this, which is not correct, right? So this is the what? Normally open, this is the normally closed. Oops. Okay guys, so and these guys should be, they shouldn't be solid, they should be dots indicating it's a terminal. So what do we want this thing to do? Okay. So that means what we'll do is our normally close should be over here, right? Are we okay? Okay. So that means when it gets to the top, it'll open up the circuit. And then we got over here, this should be our normally open. And then we got a relay coil over here. Now, what they've done is they've come over here and put a seal-in circuit so the circuit's right. And then we're putting an indicator light right here. I don't know what color. And if this is CR, whatever it is, then this right here would be CR2. Now, why do we need the seal-in? Well, if the material's above it, then it's always going to be closed until it comes up here and hits the top one. As soon as it hits the top one, it's going to open up the circuit, pump's going to stop running, and then it's going to start dropping down. This guy up here is being held up, right? And it comes down here, it breaks the circuit, right? all I'm saying. So what's gonna happen?
Don't stop pumping. Like when you break this one down, it's gonna fall.
It's gonna stop pumping, right? I'm saying. Okay.
So, when they close, normally open close, it's actually involving pumping.
Yeah, but we gotta figure this out. What's it need to sit in circle and what's gonna happen? Okay, so we got level, and I might be wrong, but we got level, right? So we're sitting right here. So this means there's material in the hopper. Okay, and we're above this sensor down here. Okay, so we're above the sensor right here. So it comes in, seals in. Are we okay? And then the level starts doing what? Going up. As soon as it hits that one, it's going to break this. It's going to open this circuit, seal in. It's going to be in. This guy right here, it's going to open the circuit, right? Pop. This guy right here is still closed. So this guy here is still closed because we have material. So as soon as we drop down below that level, what's going to happen? Yeah, it's going to close the one at the bottom, which is going to seal it in again. So what's going to happen? Yeah, I think we're going to modify the circuit. Y'all see what I'm saying? Yes or no?
Yeah.
Okay, so what's going on? Yeah, so what happens is that once it gets above the level, oh crap. Okay. So this right here is a normally, this guy here is a normally closed. I'm okay there. Oops, wrong way, Rich. I'll get it in a minute, guys. So this is the normally closed. This is the normally open. And then we have a relay. Let's go back to the actual diagram. Dang it. Oh my goodness. I'm going to figure out how to get that back on there. My Alt key just stuck. It will, but I can't draw on my PowerPoint. My PowerPoint's got to be active. So if my PowerPoint's active, I can't put two things on the screen at the same time. So we have a control relay.
It's not sealing.
It's sealing by the motor. That's where my problem is. So the motor huh? This is a seal in, but it's sealed in by the motor, by this guy right here. Okay. Now normally when we do a seal in, we come over here and we seal it in with CN. Right? Here we're sealing in with the motor. So this is normally closed. This is normally open. Right? So we have material, so this will be closed. This right here will close. That's going to close that. The pump starts pumping and puts material into the tank. Okay. Comes up here, fills up, opens this up. What's that going to do? How's it gonna stop the circuit?
That opens
But M is still energized. No,
Oh,
okay. No, that's gonna do it. This is gonna kill it. You're right. So we come up here, we get up to the high level. This opens up, drops this out. I mean, it don't drop this out. I'm sorry, drops this out, drops out the motor. The motor opens up that contact, and it does what? Drops out. Okay. As soon as it drops down below that level, this guy right here does what? Closes. This guy right here is already closed. That's what my problem is. Right. But the problem is, as long as we're below our load sensor. I'm sorry, as long as we're above our load sensor, this guy right here is going to be closed.
Yeah.
All right. So I come up here and I fill this up. Okay. It hits this guy. It drops it out. Okay. Pump turns off. We start dropping down. As soon as I drop down, this guy right here is still closed. What's it going to do? It's going to energize again. And it's going to do what?
This depends on how far apart we are.
It don't make any difference how far it is. What's going to happen is it's going to come up here and oscillate.
So it's not going
Because this guy here this guy right here is always closed. We got to come up with a different circuit.
So take the time.
Could use a timer, but then we're again tied to the discharge rate on how fast we pump it out. So if you put a timer in there, this guy right here, that might never be made, right? But we could put a timer in there, but
I think it's next.
no, that's the last circuit. It's a troubleshooting where the PPE measure the voltage, simulate a liquid in the tank by raising the active, hold the button, level switch, still holding the bottom switch, activate it, simulate the level in the tank rising, did the motor start, simulate the level in the tank lower and below, simulate the level in the tank lowering, test your verifiers. Is it working properly? You're probably going to say what? No. Yeah. Redraw the circuit in figure 2, adding a 3-position selector switch that allows the circuit to operate in 2-level control auto position and include a push button that energizes the pump motor anytime it is pressed and held down when the switch is placed in the hand position. When the push button is released, the motor turns off. Also add a red light on hand position, add a green light that is on, lamp, no lamp. Check to make sure the main power module is turned off, and that's everything we're going to do. But to me, it don't look like this circuit right here is going to work. You don't understand why? Everybody understand why. Okay, I can't draw on this one. I can, but I can't remember what keystroke it is. So the operation of the circuit would be the same whether we sealed in with the motor contact or whether we sealed in with this contact, right? And why they're sealing it in with the motor contact, I don't know. And then down here they're putting a CR, so they're calling it CN. And then they're coming down here and they have a motor starter. And they're sealing this in. So what happens, this is the problem we have, and they're using M, right? So what happens is that we're above the minimum. So if we're above the minimum, then what's going to happen? No, this guy right here is going to be what? Close. So we come over here, we reach the maximum level. This guy right here, open. Or this guy did. Stage closed. Right? So this guy drops out. Right? You understand? And then what happens? As soon as we drop down below the upper level, this guy closes again. This guy is still closed. Energizes CR and breaks the motor. So that's going to be a how. I'll look at it and see if we can figure out something to do. But I don't think this is a design project like the one you have. We need to figure out how to make this thing drop down to the lower level. So what we're trying to do is we're trying to come up with a control where it'll fill up to the upper level and then turn off, right? You understand? And stay off until it drops down to the lower level, turn back on, right? You understand? We got any ideas? But we're fixing to go left. I think we're going to have to do it with, we ought to be able to do it with two controllers. I don't think we can do it with one. 1 cent in high, 1 cent in low. All right, guys, y'all got any questions? So we know, but, so what is two-level control? That's when your control is supposed to do what? Set a range. A pump control or charging system maintains it at a high level, right? You understand? Right? A discharging system basically tries to maintain it, not maintain it, indicate when it gets to a low level. A charging system is when it gets to an upper level. A discharge system is when it gets to a low level. And then a two-level control is maintaining it between an upper and one lower level. We're going to use a normally closed and normally open limit switch, no doubt about it. It's just we got to figure out how to keep the motor, how to turn the motor off to get to the bottom, no matter what the discharge rate is. And then when we get to the bottom one, turn it back on until it gets up to the turn it off at the other one, upper one, turn it off when the lower one opens. So we want to turn it off when the lower one opens, right? We want to turn the motor back on when the lower one opens. We want to turn it off.
Right to the top.
Huh? When you get to the top. What's that? Both of them's got to be closed for it to turn on. Okay, in this diagram. But the problem we have is anytime we're above the minimum. So if I'm at the maximum, I'm definitely what? If I'm at the maximum, I'm definitely above the what? The minimum. This guy right here is going to be closed anytime I'm above the minimum. Okay. This guy here opens when I get at the maximum. So what happens is that we start off, we have material in the thing. This guy right here closes. This guy's already closed because we're above minimum. That energizes this. That brings in CR. That energizes M, and my pump motor starts running. Right? So it comes up here, my material fills up. It comes up here and opens this. I'm above the maximum. Okay, so I turn my pump motor off. Right? You understand? No following so far?
Yeah.
And then it drops down below that sensor. This guy here closes. This guy right here is still closed. Why is it still closed? Because I'm above the minimum. And then it'll fill back up. So what's going to happen is going to act just like we talked about before, where it's acting like a charging system. So what we want to do is we want to turn it off when it hits the maximum and turn it back on when it hits the what? Minimum. That's what we want to do. It's going to be hard to do that with one lump. Everybody want to understand what I'm saying? So anybody got any ideas? Huh? Well, we might not need a seal in, but what we're going to have to do is we're going to have to come over here. And this is what I have in my mind. So this is the we could probably do it with two normally open, but we'll do it. So at the top we got a what? Okay. Normally close it, it's just got a touch. And at the bottom we got a what? Normally open. Then what are we going to do with our motor? We might need to, let's see if this works. CR2 might need to be one. No, it's going to be normally open. That might be right. Nope. I need to think about this. But it's going to be something like this. So we're going to have something down here where both of them have to be made. You're right. I don't think we might not need that still. So right now we have material. This will be closed. So that would be closed. The motor would come up and run. Then it comes up there and gets to the top one. Okay. We'll open up this one. This one's still closed. So we got to figure out that's how to work. But we'll figure it out. All right, guys, you okay? Like I said, we'll work on it. But it's going to have to be something like this. Turn the lights on for us. Got a couple people that's going to be working on their own, right? So this is the configuration for my high-speed counter. I'm thinking advanced PLCs, I'll probably show y'all something. Okay. This is not the high-speed counter, right? This is the configuration for that. We have it counting for 1 second, we have it off for 1 second, counting for 1 second, off for 1 second, counting for 1 second, off for 1 second. When it turns off, I come over and I move the actual count. This is the actual count. Coming off my code. and then I take that count and multiply it by my transfer function, right? And then it comes up here and shows me the what? Yard chart. So the program itself is fairly simple once you understand the concept of how to count. This is why, instead of using all the math, I could have done it. I could have did the math, did the division, did the multiplication, but I went ahead and figured the transfer function of the whole system. Real number. This is a real number. In Allen Bradley, you have data files that are dedicated to certain things. What we do when we multiply, since Siemens decided to come up here and leave the memory open, so I'm offline. So I can go right here, and what I do is I specify the type of math I want to do. I can do integers, I can do double integers, I can do real numbers, I can use double long, quad, these are quad unsigned numbers, unsigned integers, and I forgot what it is. This is signed integer. This is 16 bits, this is 32 bits. I can't remember what that was. But what, instead of it being dedicated, you understand? And so what we do in the 500 is we have data files that are dedicated to floating point numbers, integer numbers, counters, and all that other kind of stuff. What they do in Siemens is they leave the memory open, and then you assign how much memory you need. So if I need more floating point, I can just use call it a real number or a long real number. This is what we call a long real number. That's a quad number, so that's 64 bits. We're talking about 1 times something times 10 to the 308 power. But if you go that big, you're losing a lot of resolution. But we can deal with extremely long numbers with the AL. So we're dealing with real numbers because this right here is a fraction, so I can't say it was an integer. So I told my multiply command that I was dealing with one. Now you can leave it on auto, but I had problems with auto. Auto is supposed to try to figure out, depending on what operands you bring in, auto tries to figure out what you need. But I had a problem with that. So I switched it over to what?
Sorry.
Yeah, this is the new CD value. This is the loaded value. This is when you configure the counter, it assigns it an address. Okay, it assigns it an input address. You can change that, but since this is an input port, what we can do is we can put it where we want it. So we want to make sure it's out of range. It automatically assigns it 1,000. So this is the accumulator. I gave it this tag. But if we went back and looked at the configuration of the timer, which probably wouldn't make. So here's the way we configure our PLC. And this is my high-speed counter. And when we start going through the high-speed counter, then we got general information. Then down here we got what? IO address. So the IO address it assigned it was what? 1,000. It automatically takes 2 words. But this is the address of the actual accumulator.
Okay.
This is calculated for you once you sign that. So if I called it 2,000, then this would be 2003. I don't have any control. So this is the address I use to and then we have different types of hardware counters. So this is the hardware identifier. It's 259. You can't change that. But you have to identify which type of high-speed counter you're using. So that's this input right there. So that says I'm using a type 259 high-speed counter. And you would look at that, depending on what version of the CPU you have. And this right here says I'm going to reset the counter to whatever value comes into here. But we can put any value you we want to. So we could literally set a range, right? So we might not want to reset it to 0. We might want to reset it to 5 for some reason. So then it would count from 5 up to wherever we stop it at. And the range on these things is unbelievable. Up to 2 billion. I don't think we'll be able to count on. So that answers your question?
Yep.
So this address right here is the address of the actual accumulated value. This is the output. This indicates if I had any problem. So I'm not using it. But in my multiply, I would capture it. So what happens if I had a problem, like I put the wrong numbers in, or I exceeded the range, then this right here would go through. Then I would monitor the bit inside this memory. If I had a problem, I might display an error on my HMI panel saying, you got an error, and I know what type of error it is. I know I'm having problems with this type of error. So this right here is inquiry. That's if you have any error. My move instruction, I just left it down here. I decided to. Does that make sense? So that's the program, guys. For Alan, what we'd have to do on the RS Logics is we still have a command that we configure the high-speed counter. But then again, what we would have to do is we would have to set up a timer to do this for us. But all we do is just set up a 2 hertz timer and it works the same. Because the 1100s does not have a 2 hertz time. It's got that timing register available, but it's working off a clock, and so the times are all weird. Does that make sense? Where this PLC actually set up true 2 hertz for you, where you can actually use 2 hertz, you can use 1 hertz, you can use 0.1 hertz. But on RS 500 they don't have it. But it would be basically exactly the same except for what? I would put a timer and have it timed for what? I'd have it timed for I'd have it timed for one thing. And then I'd cross them the same way. And then down here, I would have to use one of my F8 registers here because I'm using fractions. Here, Siemens, they don't assign the memory to any data register. It's up to the user to assign the memory inside the disk. And what they do on the 5000, I don't know. Like I said, I need to start learning that. The new book that we're getting with PLC has a chapter on the RS Logic 5000. Probably when I start doing that. And what we're doing here, though, is this gives us the ability to actually watch the flow, monitor what's going on inside the program. So right now I'm running my motor at 8 RPM. And the maximum we should run it at is 80. It's pretty easy. And this is the advantage of a DC motor, guys, over an AC motor. An AC motor is still hot. We can control it, but not as precisely as we can control the DC motor. And this is a really good motor. It sits almost right where it's supposed to. The one that I made wobbled, so it's so we can verify that my program's working right with this formula. What's that? The motor's turning fast, but we're going through a gearbox, right? You understand? So that's why we had to do that. That's why we had to do that 131.25. Because that's the ratio of the gear, and it's a torque, and it's a torque. Yeah, so I can't stop this with my finger. I can't turn it with my finger either. Now I could come back here on this encoder, and I could just barely touch it, and the motor would stop. So it's a low torque motor. So if we increase torque, we decrease speed. If we increase speed, we decrease torque. And anybody that's rode a multi-speed bicycle understands that, right? Like I said, here you're going up a hill, and you go down to the lower speed. You're sitting there pumping like crazy. You're just barely going up that hill, right? You understand? Because what you did is you decrease speed on the output, and you increase because you're going to a torque multiplier. So we don't get anything for anything. We don't get anything from nothing. And work in equals work out. So if work is equal to speed times torque, and my input speed times torque, and my output speed times torque is supposed to come up and give me the same answer, right? You understand that? If the torque goes up over here, speed's got to do what? Got to go down. And that's the concept. When I learned that, and there's so many things that just started making sense. That we don't create energy. All we can do is do what? Change its form. Energy in equals energy out. If what? If the system was 100% efficient. There's no such thing as anything that's 100% efficient. So your output work will always be less than your input. But for calculations, what we do is we can say, okay, I can take my input, and if I go through that ratio, I could divide it by 131.25, and then that would come up. Then I would multiply that by the efficiency of the motor. Motors now, that's part of the nameplate on the motor. They have to specify the efficiency of the motor, and that's how much you lose inside the water, inside the motor. So, good quick. So what should be the time? We'll check it on our oscilloscope for 80 hertz. Yeah. 80 RPM, excuse me. So what should be the time on my oscilloscope for 80 RPM? So what we can do is we can verify our program, even though I've already done it. What's so nice about a function generator is it shows you the frequency. And I could come up there and I could set the frequency. I calculated for 80 hertz, and this program said 80 hertz. But what we need to do is we need to verify. So let's get it as close as 80 as I can get. So that's pretty dang close, right? I think I can go a little bit. So what should be my time for 80 hertz? Or 80 RPM. So maybe the formula. So you just take this and divide it by RPM, and that should give you my time. So I've already transposed that. We could very easily do this with the PLC. If I did this, I could do this with the PLC. Don't understand that. This would take 2 instructions. This would take multiply, then you have to have a reciprocal. That would take 4 instructions. This right here would take this one. I modified this formula too, guys. This would be 1 times 60, but what I've done here. You can take any of these and move it over there if you want to, right? So 0.0286 divided by, what's our output frequency? 80. And I have to apologize, my Alt key has come off. And that's the way you go between programs. So I got my oscilloscope set on must have gone above. So we'll increase it by 1. So I've got 50 microseconds per division. That'd be 5100. That'd be 5200. That'd be 5300. About 350 microseconds. Show calculator. Huh? Yeah, it's over a hair. It would be hard to see. And it must not. I think I got it slightly less than 8. So what we've done is we verified our program, right? And we verified our calculations. And what's nice about an oscilloscope, guys, it shows you what. A meter can't do this. So what's nice about an oscilloscope, it shows you exactly what's there. So that's one, and it's voltage relative to time. I'm trying to get my camera to focus. These guys are neat, but I still miss the manual focus that we have on a regular camera. It still can't do it. So 500 microseconds, 1, 2, 3, 4, 5, 6, 7.2 divisions, multiply it out, it should come up to be a little over 350 microseconds. Okay. So that's, getting at PLCs, that's a little interesting thing, but the advantage of a PLC over electrical controls is what? You're right. One of the big advantages is we can change things without. But I could not do this with electrical controls. Electrical controls cannot do math. Right? You understand? They have some pretty dang high-speed counters because in motor controls, the counters are mechanical, right? I mean, they are solid state now. But I could not do the math. So I could not do this with motor controls. I had to do this. I have to do this with a computer, right? Okay. That's neat. I'm trying, it looks like it needs, looks like my PLC. Two, 4, 6, 8. Looks like it needs about 9 to 10 volts to stop working. Yeah.
South. Cop. The labor from the cop.
Gary, y'all was waiting on some type of sign off? Yeah, we're in lab here, right? Y'all working, y'all know y'all working on another class, right?
Well, I'm just trying to find out what we can do.
But still, that's outside of this class. I can understand that. That's another class. I'm gonna go back here to Milton. I'll come back.